Hello, dear students. Today we are going to learn about series and parallel connections. What are the series parallel connections? Okay, so in an electric circuit, series connections in an electric circuit. Series connection in an electric circuit. Electric circuit. Alright, in an electric circuit. Okay, so we have that's our topic. Series connection in an electric circuit. So first of all, what is a series connections? Let's say we have got a certain resistance. We have got some resistance. Let's say this is a symbol of a resistance. Let's say this is the first resistance. This one is the second, and this one as the third resistance. Alright, if we try to connect end-to-end connections, alright, if we try to connect the end of the first one, if we try to connect the end of the first one to the start of the second one, and again the end of the second one to the start of the third one, and let's name this distance as, let's say, this one as R1, this two as R2, and this one as R3. Alright, so this is the kind of connections which is called the series connections. The end of the first one is connected to the start of the second one, and the end of the second one is connected to the start of the third one. So this, if we try to connect these resistance in this way, we call it a series connections. Alright, now let's for the flow of current, we need to close the circuit and apply certain potential difference so that the current may start to flow, and we can calculate the amount of resistance in the given circuit. Alright, so let's close the circuit. So I'm trying to close the circuit using a cell of a certain potential difference, and we close this circuit. Alright, let's say this battery has a voltage of V, or you can say that the potential difference across the cell is V. Alright, when we apply certain potential difference, then the current will start to flow. Alright, because since this is a series connections, and there is only one path for the flow of the current, so the same amount of current will flow through R1, the same amount of current will flow through R1 also, and the same amount of current will flow here, the same amount of current will flow through R2 also, and the same amount of current I will also flow through R3. Alright, so this is how the current will flow. That means the current is not going to be distributed, but at the position R1, there might be certain potential drop, let's say between these points, okay, between these 2 points, okay, let's name this point A and B. Alright, so between A and B, because there is a resistance R1, it will use some amount of energy. So let's say the amount of potential drop is V1 over here. Let's name this as V1. Across R2, let's say the amount of potential drop is V2. Alright, and across R3, let's say the amount of potential drop is V3. Okay, so this is how the potential will be divided. That means this whole potential difference will be divided into 3 components, such that we can say that the total V, this total V will be equals to V1 plus V2 plus V3. As we see that the amount of current flowing through the circuit is same, and there's only the potential is divided into 3 parts. Let's say V1, V2, and V3. The V1 is the amount of potential drop across R1, and similarly for V2 across R2 and V3 across R3. So from Ohm's law, we can say from Ohm's law, we can say that okay, now that's this side. Okay, now from Ohm's law, we can say that we know that V is equals to I into R. Okay, from Ohm's law, we can say that V is equals to I into R. Alright, so putting for this V is supplying voltage to all 3 resistance, so let's say that the equivalent resistance is Re. Okay, so we know that V is equals to I can say from this equations, let's name this equation as equation number 1. From this equation, I can say V is equals to IR. Okay, so I into R E. So IE stands for the equivalent resistance in the circuit. Alright. So that will be equals to, for V1 I can write I into R1 less I into R2 for the second resistance, and I into R3 for the third resistor. So since the amount of current flowing through all the resistors is same, so I can take I as common. Here I take I as common, it is R1 plus R2 plus R3. Okay, so from here I and I got cancels. So the equivalent resistance in case of series is equals to R1 plus R2 plus R3. And here all three resistors, all the three resistors, they are all connected in these all three resistors, R1, R2 and R3, they are connected in series. So this gives you the value of the net equivalent resistance across a circuit in which all three resistors are connected in series is given by R equals to R1 plus R2 plus R3. I hope you understand how we come to this equation. So this is a very important equations for calculating the amount of equivalent resistance in case of a series connections. Now let's come to the parallel connections. Okay, the parallel connections. Okay.
क्यों आज नहीं
हाँ?
क्यों आज नहीं
ना कोई।
अच्छा अच्छा सुन ले
हाँ सुन हाँ वो अभी दिया है। Now let's come to parallel connections. So what is a parallel connections? Let's understand. Okay, what happens when you try to connect three different resistors? Let's say we have three resistors. Okay, R1. Okay, let's name this as R1. This one as R2, and this one as R3. All right. So we have got three different resistors. Okay, and how to connect them in parallel? To connect them in parallel, what we try to do is we try all the starting points of all the resistors are connected to the same wire. Let's say, okay. So all this is starting through the same start. Through the same start, all the three startings are connected, and through all the ends are connected at the same wire. Okay, the start of all three resistors are connected to the same wire. The end is also connected to the same resistors. Okay, so such type of connection is called parallel connections, where the points of let's name this as the point A, and this one as point B. So at A, all the starts of the resistors connected, and for point B, all the ends of the resistors are connected to the point B. So such a connection is called, you can say, this is a kind of a parallel connections. Alright, so how to actually calculate the equivalent resistance in case of parallel combinations? Alright, so what I am trying to do is, let's close the circuit in order to let the current flow. Okay, let's make it here. Alright. So how do we connect the circuit? Let's close the circuit. Alright, to close the circuit, we'll try to apply, okay, so this is a circuit here over here, and I'll try to apply voltage through a different, okay, let's say voltage V is applied plus and minus 2, so the potential difference. So when you apply a potential difference, the current will start to flow. The current will start to flow. So same amount of current will be flowing over here, but what will happen here, this is the point. This point is called the node. Okay, this point is called the node, or you can say junction. So at node or junctions, the amount of current that's flowing in the circuit divides. Alright, let's say some amount of current flows over here. Let's name it as I1. Some amount of current flows here, okay, I2, and some amount of current flows here. Let's say it's I3, and so the total amount of current was flowing was I. So this I was divided into I1, I2, and I3. So from here we can say, with simple additions, I can say that the total amount of current that was flowing through this cell is equals to nothing but it is I1 plus I2 plus I3. Alright, so now what will I do? I'll follow the same step as in case of a series resistors. I will try to write using Ohm's law. We can say using Ohm's law, using Ohm's law, we can say I is equals to V. We know that the equation is V is equals to I into R. Alright, V is equals to I into R. So for I can write I is equals to nothing but V upon R. Alright, so this is what I'm going to use now. Okay, so here I put this one here so that it's more visible. Okay, so now what I'll do is this V, I is supposed to be upon R. So for this equation, okay, so for this equation, let's name this equation number 1. From here, this I can be written as V upon R. Okay, this I can be written as V upon R. Alright, so I1 will be nothing since these all resistors are connected between only 2 points. Their potential difference will be same. So I1 will be nothing but V upon R1 plus I2 will be V upon R2 and I3 will be V upon R3. Alright, so we form this equation. Since the potential difference across all the 3 resistors is same, we can cancel out the. Alright, so taking V as common, okay, now we finally come to the equations. 1 upon R is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. And this equation is, okay, so this is a very important equation. This is a very important equation which helps you to calculate the equivalent resistance. This helps you to calculate. So this R is nothing but you can see the equivalent or the net resistance, equivalent for net resistance, in this parallel combinations in parallel combination of resistors. Okay, in parallel combination of resistors. Alright.
Right.